Okay, so now I'm going to continue the thread of the conversation. So I didn't get to any new stuff. I don't know what happened with the microphone. Next reaction that we want to talk about is hemiacetal formation. Okay, so the recipe for making a hemiacetal is very similar to the recipe for making the hydrate. We're starting, will be the overall reaction. You're starting with an aldehyde or a ketone. Aldehyde or ketone. And this time, instead of adding water, which is HOH, we're going to allow the aldehyde or ketone to react with an alcohol, which is ROH, right? This is an alcohol where the R group will be some kind of organic group. So notice, compare water, right? Water is HO, H-O-H. All I'm doing is replacing one of the hydrogens in water for an organic group, which I'm calling R. So R can be a methyl group or a benzene ring or whatever. The reaction is once again reversible. It happens under acidic conditions or basic conditions. So when the reaction is under acidic conditions, you're going to see an H plus above the arrow. It's exactly the same thing as we saw with hydrate formation. But now, when the reaction conditions are basic, instead of seeing OH minus, what you're going to see is OR minus. So once again, just compare to what we saw under basic conditions, which was OH minus. So all I'm doing is I'm taking the water molecule, HO, HOH, and replacing one of the hydrogens in water with an organic group. The product is very, very comparable. So remember, the hydrate is going to have an OH up there and an OH down there. Now, when the aldehyde or ketone reacts with an alcohol, what we're getting is OR on one side of what used to be the carbonyl and OH on the other end of what used to be the carbonyl. This thing is called a hemiacetal. Okay, and remember, a hydrate has a carbon atom with two OHs. A hemiacetal is going to have a carbon atom with an OH and simultaneously bonded to an OR. Okay, so that's hemiacetal formation. It can happen under both acidic conditions and basic conditions. Let's just do some product prediction and then we'll talk about the mechanism. All right, so what if we have something like cyclohexanone? There's the aldehyde or ketone, and react that with ethanol. Let's say that, okay, the reaction is reversible. If it happens under acidic conditions, we would have H plus above the arrow, but now, if it happens under basic conditions, we're going to have the conjugate base of the alcohol. We're going to have this ethoxide underneath the arrow. Okay, the product here is going to be what? Okay, so you try it. Let me give you a minute. You're just using this model here. Predict the product of the reaction. It's a hemiacetal. Okay, the carbonyl carbon, I'm going to put a dot on him. The carbonyl carbon ends up with an OH on it and the alcohol minus the proton, right? It ends up with OR. It ends up with this, whatever the structure of the alcohol was minus a proton. So that would be the product there. That's the hemiacetal. Did you get that? Okay, so let's see. Let's try another one. All right, so what about this aldehyde? That's benzaldehyde. And this time let it react with isopropyl alcohol. The reaction is reversible. It happens both under acidic conditions or basic conditions. Acidic conditions, you're going to see an H plus above the arrow. Basic conditions, you're going to see the conjugate base of the alcohol above the arrow. Okay, draw the structure of the product. Okay, so why don't you take a minute and see if you can come up with the structure of the product. It's going to be a hemiacetal, where the carbonyl carbon, or what used to be the carbonyl carbon here, now has a an OH group, and what is left of the alcohol minus a proton. All right, so what will this hemiacetal look like? Okay, so there's the carbonyl carbon. It has an OH on it, and it has the alcohol minus the proton that the alcohol came in with. Okay, so that would be the hemiacetal. This is the product of an aldehyde turning into a hemiacetal. The previous problem was a ketone turning into a hemiacetal. Let's just try one more. Okay, so how about if we have this plus, let's add methanol, CH3OH. The reaction is reversible. It happens under acidic conditions or under basic conditions. Under basic conditions, you're going to see the conjugate base of the alcohol. And so we get something that looks like that. Okay, so what would be the structure of the product? So this is the recipe for a hemiacetal. It's an aldehyde or ketone plus an alcohol plus acidic conditions or basic conditions. The product here is going to be a hemiacetal, which means that what used to be the carbonyl carbon ends up bonded to OH and to the whatever the structure of the incoming alcohol was minus the proton. Okay, all right, so now let's talk about mechanism.
Wait, when you write the like the CH3 OCH3,
Yeah.
can you write it like in any order?
Well, no, because what you want to express is that the oxygen was the attacking nucleophile. So what I just erased, I think maybe I wrote something that looks like this.
Mm-hmm.
Okay, so now in any order do you mean, is this okay?
No, I just more meant like I know the O has to be bonded first because it's like bonded to the O, but the C and the H, can those be in any order?
The CH3?
So if you like, could you do OCH3 or OH3C?
No, because if you drew out every single bond,
Oh, okay.
like this, right?
Yeah. Okay.
It would look like this. And so it's it was very good of you to realize that the oxygen has to be bonded to this carbon, but then the rest of that molecule has a carbon atom, and the carbon has the 3 hydrogens.
Okay.
So I don't know if you write OH3C. I don't know, what does that mean? Oh, does that mean this?
Yeah, okay.
No. So no.
Okay, thank you.
Okay. All right. So now let's talk about mechanism of hemiacetal formation. And first of all, let's talk about mechanism in acid. It's exactly the same as the hydrate mechanism, except instead of working with water, instead of working with HOH, we're going to work with ROH. All of the steps, all of the thinking are exactly the same. Okay, mechanism in acid. There's our aldehyde or ketone, and we have said before that anytime we see an aldehyde or ketone or any kind of carbonyl compound in acidic conditions, the first 2 steps of the mechanism are nearly always going to be step 1, protonation of the carbonyl oxygen. Step 2, attack by the nucleophile on the carbonyl carbon. So whenever we see a carbonyl compound plus acidic conditions, these are the first 2 things that nearly always happen. Protonate the carbonyl oxygen, then attack the carbonyl carbon with the nucleophile. Okay, so I'm trying to be very good about how this is reversible. The first step in the mechanism would be this oxygen atom has 2 unshared pairs of electrons. It functions as a base. It picks up a proton from the solution. And so we have a species that looks like this. Okay, and the reason that this happens is because the alcohol is the nucleophile. The nucleophile is electron rich. Electrons are negatively charged. A nucleophile is more attracted to something that is positive than to something that is neutral. Okay, so we could write a resonance structure. Don't have to do this, but maybe it makes what happens next a little bit easier to understand. We could write a resonance structure where we're showing that that oxygen atom is gobbling up the electrons in the in this double bond. There are 4 electrons here. The oxygen is gobbling up 2 of them. This oxygen atom started life with 2 electron pairs. At this stage, it has 1 electron pair because it used 1 electron pair to snag the proton from the solution. And now when I do this resonance move, that oxygen is back to having 2 unshared pairs of electrons, and it's neutral. Where did this extra unshared pair of electrons come from? That came from this carbon-oxygen double bond that oxygen is withdrawing because it's so darn electronegative. Okay, so first step, protonate the carbonyl oxygen. Next step, attack the carbonyl carbon, this positive charge, with the nucleophile. So just to save time, instead of rewriting all of this a second time, what I'm going to do is I'm going to show the next step this way. Here's the alcohol. That's the nucleophile. That oxygen atom has 2 unshared pairs of electrons on it. I'll draw both of them, although remember, I never have to show an unshared pair of electrons. That's the nucleophile. That's the electrophile. The oxygen attacks the electrophile. Okay, continuing, concluding over here. Now I have OH. The oxygen came in, it formed a bond to the carbonyl, and this oxygen has to have a positive charge. Where are all of these charges coming from? Remember the first day of school, right, where we presented that valency table, and we saw that when an atom forms each atom forms a characteristic number of bonds with a characteristic number of characteristic formal charge. This arrow means the oxygen, the electrons on this oxygen are attacking that carbon. Okay, and so the last step of the mechanism is going to be the deprotonation of this positively charged oxygen. Oxygen doesn't like to have a positive charge because oxygen is very electronegative. Rather than sharing the electrons with this proton, it wants to own them. So something comes along, a base comes along and removes that proton. And so that proton goes flying off into the solution. It's never heard from again. This means minus H plus. And we see the reaction is catalyzed by acid. A proton got everything going. And in the last step of the mechanism, the proton, the catalyst, is spat out. And there is our mechanism for acetal formation under acidic conditions. It's exactly the same as the hydrate mechanism, but instead of HOH, I'm just writing HOR. Okay, so that simplifies matters somewhat. It's not an entirely new mechanism. Okay, so now let's talk about mechanism in basic solution. And once again, this is exactly the same as the hydrate mechanism, except that we're using ROH instead of HOH. There's our aldehyde or ketone. Its basic solution, we don't have any protons around, so H plus is not involved anywhere here. What will happen here is that the RO minus dot 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 with a negative charge here. That's the conjugate base of the alcohol. The carbonyl carbon is the electrophile. That O minus is the nucleophile. The nucleophile attacks the electrophile directly. We can't stop there, because if we do, we'll have a carbon with 5 bonds. So the alcohol attacks the carbonyl carbon, and we get a species that looks like this. Okay, so this is exactly what happened with the in the first step of the hydrate, except with the hydrate we had OH minus here. Now we have RO minus. Okay, and so now second step, the alcohol functions as a proton source because there is no H plus around. We're under basic conditions, and the electrons around this oxygen grab a proton from the alcohol, and the electrons that were keeping the H bonded to the oxygen atom in the alcohol are gobbled up by the oxygen atom. And so we get RO minus is produced. And what we really care about is the hemiacetal that was manufactured here under basic conditions. So again, it's exactly the same mechanism as we had for hydrate formation, except that we're using an alcohol instead of water. Okay, so that's the basic, that's the fundamental information about the hemiacetal. But now we have to get into some subtleties and to some difficulties and to stuff that is a lot more challenging. This is these are features of hemiacetal formation that hydrate formation didn't have. First up, stereochemistry. The stereochemistry of hemiacetal formation? Well, we didn't have this issue with hydrate formation because in hydrate formation, a new chirality center was not created. In hydrate formation, what used to be the carbonyl carbon ends up being attached to two OH groups. That's not a chirality center. But in but when we form hemiacetals, well, we have to entertain stereochemistry. All right, so let's look at a simple example to start off with so that we can see what the issues are. Okay, so there's an aldehyde or ketone. I'm going to make a concrete example here, put CH3 there and CH3 there, something like that. And we see that this carbonyl doesn't have a more reactive face and a less reactive face. This carbonyl, the nucleophile can approach from the front and from the back with equal probability along that Bürgi-Dunitz trajectory. So let's say we react this guy with methanol, and we could do this under acidic conditions or basic conditions. Let's just do it under acidic conditions. And so we're going to get a hemiacetal, but the nucleophile could have come in from the front or it could have come in from the back with equal probability. So that means that we're going to get a product in which 50% of the time the nucleophile, the methanol, came in from the front, 50% of that, and 50% of the time, the nucleophile came in from the, something's wrong here. This should be OH. And 50% of the time, the nucleophile came in from the back. Okay, so what I've pictured here, this 50% here. So how are these two guys related, right? I'm trying to show how the nucleophile came in from the front and from the back with equal probability. How are they related? Are they identical structures? Are they enantiomers or are they diastereomers? Anyone want to give it a shot?
You forgot.
What?
You forgot the OH group on the second structure.
Oh. Thank you. Yeah, I'm very stressed out, very nervous. Okay, so what about those guys? Are they identical structures? Are they enantiomers or are they diastereomers? Anyone want to give it a shot? They are identical structures because a new chirality center was not created. That's not a chirality center. It has two methyl groups on it. That's not a chirality center. It has two methyl groups. Yeah, I put all of this dashing and wedging, but it's essentially meaningless because there's no new chirality center. So in this case, we got identical structures. We don't really have 50% of one thing and 50% of something else. We actually have 100% of the same material. Okay, so what we've just seen is that hemiacetal formation can sometimes give you one and only one product. All right, but now I'm going to change this up. I'm going to change this up ever so slightly. I'm going to put benzene on one side. I'm going to put a phenyl ring on one side, and I'm going to put a methyl group on the other side. And once again, react this with methanol. This could happen under both acidic conditions or under basic conditions. And and we see that this ketone here is it doesn't have a more hindered face or a less hindered face. The nucleophile can come in from the front or the nucleophile can come in from the back with equal probability. There's nothing in the way of the nucleophile in the front. There's nothing really in the way of the nucleophile in the back. So I'm going to try to remember the OHs this time. So we would get 50% of the time, the nucleophile could have come in from the front, and 50% of the time, the nucleophile could have come in from the back. Okay, and so there are the products, that would be the products of this reaction. Okay, so now look at these two and how are they related? Are they identical structures? Are they enantiomers or are they diastereomers? Anyone want to give it a go?
Enantiomers?
Oh, these are enantiomers because I've created a new chirality center here. That didn't happen here. That's why I got identical structures. These are going to be enantiomers. There's a new chirality center here. Let's try to figure out the R and the S. So that's going to be 1, 2. Methyl is going to be last. So this is going to be 1, 2, 3, reverse. That's the S, and this will be the R. Okay, so in this case, hemiacetal formation produced enantiomers. So depending on what the starting material is, you could either get identical structures or enantiomers. And yes, you could even get diastereomers. All right, so let's look at an example where we would get diastereomers as the result of hemiacetal formation. So the stereochemistry of this reaction is kind of tricky because all of the options are possible. You have to closely examine the structure of the starting material. Okay, so let's look at an example where we're going to get diastereomers. All right, there's the ketone. And what I'm going to do is I'm going to put a methyl group here. All right, and that's a chirality center. There's hydrogen here. Let's see, what is its absolute configuration? This is going to be tied. This is going to win 1, 2, 3. That's an R absolute configuration. And now let this react once again with methanol. The reaction is reversible. Let it happen under acidic conditions. It could also happen under basic conditions. We're going to get, now see this guy, this carbonyl is, the front and the back of this carbonyl now are not equally reactive because maybe this methyl group is in the way, but that is not going to kill reactivity from the front. It's just going to diminish it, right? So it's not as if the nucleophile, because of this methyl group here in the front here, it's not as if the nucleophile can't come in from the front. It can come in from the front, but it's going to be easier to come in from the back. You're going to get both the attack from the front and attack from the back, but now you're not going to get 50-50. We can't predict what percentage we'll get just by looking at the structure. We would have to do the experiment in the laboratory. Anyway, so there's my methyl group that I started out with that had the R absolute configuration. The nucleophile can come in from the front. And it can also come in from the back, but now this is not going to be a 50-50 proposition anymore. So the nucleophile can come in from the front or it can come in from the back. In this example, it's very hard to predict what the major product will be, but it's probably going to be this one, but you just can't tell by looking at the structure. So I'm going to put a capital M there, meaning major product. We think that's what it is, but we would have to analyze this a lot more carefully. All right, and so this guy here, the absolute configure, that's a chirality center, and that's a chirality center. So a new chirality center has been created, and some of the time, this is, let's see, what would be the absolute configuration here? That's going to lose. So it's 1, 2, 3, reverse. That's the S. This is the R. Okay, so a new chirality center has been created, but now these guys are not enantiomers because enantiomers are non-superimposable mirror images. When the S absolute configuration looks into a mirror, it sees R. That's its mirror image. It's the left hand is the mirror image of the right hand. But when the R absolute configuration looks into a mirror, it has to see S, but it doesn't here, right? So these are not enantiomers. These are diastereomers. So the stereochemistry of hemiacetal formation is tricky because you could get a single compound, you could get 2 enantiomers, or you could get 2 diastereomers depending on the structure of the starting material. Okay, so let's do some product prediction and try to characterize the product as either a single compound, a mixture of enantiomers, or a mixture of diastereomers. Okay, so what about this guy, benzaldehyde plus ethanol, acidic conditions. Draw the structure of the product and tell me, is the product a single compound, a mixture of enantiomers, or a mixture of diastereomers? Draw the product. Don't draw the product with any kind of dashing and wedging. You don't have to. It will be enough just for you to tell me whether you're going to get enantiomers or diastereomers or a single compound. So what do you think you're getting here? Anybody want to give it a shot? Are you getting a single compound, enantiomers, or diastereomers? Oh, I think you're going to get enantiomers because 50% of the time, this carbonyl doesn't have a more hindered side or a less hindered side. The nucleophile can come in from the front and from the back with equal probability. 50% of the time, the nucleophile is going to come in from the front. And 50% of the time, the nucleophile is going to come in from the back. So what I've drawn there doesn't have any dashing and wedging, but I do want for you to realize that it's going to be R plus S at that new chirality center that was created, right? I didn't show any dashing and wedging here, but I'm expressing that it's a mixture of enantiomers by telling you you're going to get some R, you're going to get 50% R and 50% S. Does that make sense? Yes?
Yeah, I have a question. Why wouldn't you put the OH attached to the end of the, like the tail of the O?
Why wouldn't I put the OH? This OH?
No, the other one, like the plus. There, that one. Why wouldn't you put that on the result?
Here it is right here. Are you asking me why is this H gone? I don't understand your question.
Like why on the other example, the CH3 was written, but the, no, I get it, okay. Because it leaves once you do the result.
Correct. It's called the product. Okay, so now let's look at another example. Maybe something a lot more complicated. Right, we love this witch's hat molecule. Put the ketone there and react that with methanol, acidic conditions, draw the structure of the product, and tell me, are you getting enantiomers, are you getting diastereomers, or are you getting a single compound? So what are you going to get here? Anybody want to give it a shot? Oh, you're going to get diastereomers here because this carbonyl, does it have a more reactive face or a less reactive face? Is it easier for the nucleophile to come in from the top or from the bottom along that Bürgi-Dunitz trajectory? Well, I hope it's clear that the bottom is much more accessible than the top. In order to come in from the top, the nucleophile would have to find its way, have to work its way past these methyl groups, past that stick-up feature. And so what we're going to do, what we're going to get here are two diastereomers. All right, so I'll write these out. The major product, and here it's easy to tell what the major product is going to be. The major product had the nucleophile coming in from the bottom, right? Just because that's easier to approach. That's the major product. The minor product is going to have the nucleophile coming in from the top. So in this example, it's easy to predict who the major product is and who the minor product is. So that's going to be the minor product where the nucleophile had to come in from the top. Okay, and these guys here, they're diastereomers. They're not enantiomers, they're diastereomers. And remember, diastereomers have totally different properties. They have different melting points, boiling points, different IR spectra, different solubilities, different RF factors in a TLC experiment, just totally different properties. Whereas enantiomers have identical properties unless they interact with other chiral substances. Okay, so just to recap what we said about the stereochemistry of hemiacetal formation, it's complicated, it's tricky. You can get either a single compound, enantiomers, or diastereomers. It all depends on the structure of the starting material. All right. Now, I'm going to bring this eventually. I don't know if I'll be able to do this today, maybe on Wednesday, but I'm going to bring this all the way back to what I would think would be your world, which would be the world of someone that would be interested in biochemistry and nutrition and dietetics. So bear with me, we'll be getting there eventually, because all of this is extremely relevant chemistry to someone who wants to understand metabolism and how food is converted into energy. Okay, so the next topic to talk about a more complexity that hemiacetal formation has that hydrate formation did not have is now the possibility of intramolecular hemiacetal formation. Intramolecular hemiacetal formation. Okay, and this, like the stereochemistry, was something that hydrates don't exhibit. The recipe, the starting materials, the recipe for the hemiacetal is an alcohol plus an aldehyde or a ketone, right? Just abbreviating everything, plus acid or base. Okay, and we went through several examples of this already, but we have situations in which the alcohol functionality and the aldehyde or ketone functionality are on the same molecule. So that instead of an alcohol and an aldehyde or ketone as separate molecules reacting to form the hemiacetal, we can have a molecule that has both an aldehyde or ketone and an alcohol all in the same molecule. This is where we're going to have intramolecular hemiacetal formation. Okay, so let me give you an example here. There's an alcohol, and here's a ketone, and here's acid. Oh, that's the recipe for a hemiacetal. All we need is an alcohol, there it is, and we need an aldehyde or ketone, there it is, but now they are on the same molecule. We're going to get a hemiacetal, but as the result of an intramolecular reaction. This is normally really only possible if a 5-membered ring or a 6-membered ring can form. Okay, so so let's look at mechanism. First step, protonation of the carbonyl oxygen. Right, we said this already, that a carbonyl compound plus acidic conditions protonate the carbonyl oxygen, and then the next step is attack the carbonyl carbon with the nucleophile. Now, in the examples that we've done up to now, the protonated carbonyl has to swim around in the solution looking for a nucleophile to react with. But here, the nucleophile is just a short distance away, and so this guy doesn't have to swim around in the solution, bumping into H plus and bumping into impurity and bumping into solvent and bumping into this and bumping into that. The nucleophile with which this carbonyl must react is right there in the very same molecule. So this is going to be very fast, and not only that, but we're going to get a 5-membered ring as the product. And those 5-membered rings are thermodynamically stable, so this is very likely to happen. Protonate, all of the steps are reversible. Protonate the carbonyl oxygen, and then attack the carbonyl carbon with the nucleophile, which happens to reside in the very same molecule that the protonated carbonyl did. See this arrow? This is going to be replaced by a bond. And when I replace this with a bond, I'm going to get a 1, 2, 3, 4, 5-membered ring. And so there's the oxygen. It attacked the carbonyl carbon, or what used to be the carbonyl carbon. That proton is still there, gripping that oxygen atom. And so there's our next intermediate in the mechanism. Okay, last step of the mechanism is the deprotonation of that oxygen atom, because remember, this reaction is catalyzed by acid, and a proton got the mechanism going, and a proton is spat out at the end, and there's a hemiacetal, but the hemiacetal was formed by an intramolecular reaction. Okay, so just to summarize what can happen here for the intramolecular hemiacetal, we have OH and aldehyde or ketone in the same molecule, and very important here, and a 5 or a 6-membered ring can form. So this intramolecular reaction is highly unlikely in any other situation because a 5-membered ring or a 6-membered ring, they're thermodynamically stable. A 3-membered ring, that's just too small. A 7-membered ring is too big. There's something about being a 5-membered ring or a 6-membered ring that confers thermodynamic stability on the molecule. Okay, so here we got a 5-membered ring. And notice once again, although I didn't do any of the dashing and the wedging, right? But I hope that you can appreciate how this carbonyl doesn't have a more hindered face or a less hindered face, so the nucleophile can come in from both the front and the back with equal probability. So a new chirality center was created here. And so I do want to indicate that this is going to be R plus S at that new chirality center indicated by the star. So I get enantiomers here. All right, so now let's look at an example of how a 6-membered ring can form. Once again, the recipe for the hemiacetal is an aldehyde or a ketone plus an alcohol. But what we've just discovered is the aldehyde or ketone and the alcohol can be 2 separate molecules, or both of those functional groups can be on the same molecule. So maybe something like this. Let's see, I'm going to have an aldehyde this time. And down the line on this molecule, I have an OH group. Okay, so that's, and now just throw in a pinch of acid. And there's our recipe for a hemiacetal. It's an aldehyde or a ketone and an OH and an alcohol. But in this case, they are on the same molecule. When I hook the alcohol oxygen up to the carbonyl, can I get a 5-membered ring or a 6-membered ring? Let's see. 1, 2, 3, 4, 5, 6. Yep, I can get a 6-membered ring, so this reaction is very likely to happen. The first step of our mechanism would be the protonation of the carbonyl oxygen. We've seen that lots of times already. Protonation of the carbonyl oxygen. That makes the carbonyl carbon more attractive to the nucleophile. The nucleophile in this case is on the very same molecule, so this guy doesn't have to swim around looking for something to react with. It can react with the alcoholic oxygen that's just down the line here. So that nucleophile attacks the carbonyl carbon. That oxygen atom gobbles up that pair of electrons. I'm going to get a 6-membered ring. This arrow is going to be replaced by a bond pretty shortly. 1, 2, 3, 4, 5, 6. Yep, I get a 6-membered ring. That proton is still hanging on for dear life. You get something that's going to look like this. OH, H, positive charge on this oxygen. And then the last step of this mechanism is the deprotonation of that oxygen. Something comes along and removes that proton. The oxygen gobbles up that proton, that gobbles up that pair of electrons. That positive charge is extinguished. And so I get this thing, which is a 6-membered ring for a product of a 6-membered ring hemiacetal produced by an intramolecular hemiacetal. reaction. Okay, and once again, do I get a single compound? Do I get enantiomers or do I get diastereomers? Well, there's a new chirality center there. The original carbonyl doesn't have a more reactive face or a less reactive face, so I'm going to get 50% attack from the front and 50% attack from the back. So once again, here I'm going to get enantiomers, 50% R and 50% S at the chirality, at that newly created chirality center. Okay, so this is big. This is important. This is showing how the hemiacetal can form under can form intramolecularly, just as long as a 5-membered ring or a 6-membered ring can form, can be produced. Okay, so let's see. Maybe let's try a product prediction question. Okay, so I'm going to raise the complexity of this example by a lot. Okay, so something like that. Well, see, I was very nice here and I've drawn the molecule in a way that it's going to make it pretty, make the product maybe easier to understand. So the reaction is reversible. Let's look at this under acidic conditions. Okay, and so now in this molecule, I see 2 OH groups. So the first crisis is which OH is going to participate in the intramolecular hemiacetal? Both of them? Well, it's not going to be this one, because if I hook up this oxygen to this carbonyl, I get a 1, 2, 3, 4 membered ring. No good, right? Because this intramolecular hemiacetal only takes place when a 5-membered ring or a 6-membered ring can form. So that's an alcoholic OH, that's an aldehyde, but the intramolecular reaction will not happen because that's going to lead to a 5-membered ring. I mean, to a 4-membered ring. Okay, what about this OH? Can he react? 1, 2, 3, 4, 5. Yep, when I hook up the carbonyl with this oxygen, I'm going to end up with a 5-membered ring. Those are nice and thermodynamically stable. Is this carbonyl equally reactive from the front and the back? Probably not, because this OH group is in the way as the nucleophile tries to come in from the back. So that doesn't kill the reaction from the back, it just slows it down. So I can't predict what percentage of anything I'm going to get, but I do know that I'm going to get more of one than of the other. All right, so there's our 5-membered ring. Some of the time, the nucleophile came in from the front, and some of the time, the nucleophile came in from the back. So some of the time the nucleophile came in from the front and some of the time the nucleophile came in from the back. I can show that with dashing and wedging this way. Okay, and so now what I see, these are diastereomers. Absolute configuration here. Let's see, this is going to be 1, 2, 3, reverse. That's S. Let me check that. 1, 2, 3, reverse S. This is S. This is 1, 2, 3. That's R. This is 1, 2, 3, reverse. That's S. See, these guys are diastereomers. that formed as a result of this intramolecular hemiacetal. Okay, and the reason that this is important is because this guy here, this is a carbohydrate. This is a sugar. And we see that carbohydrates, sugars, exist, can form and exist as hemiacetals. Okay, so that belongs to the biochemistry of the carbohydrates, which we're going to talk about more extensively later. Okay, so I want to finish up there now. Any questions about anything before we go? Any questions about anything before we go? No? Okay, well, I'll see you next time. Until then, bye-bye.